Hi, guys. Welcome to Lecture 5, where we're going to cover reinforcement learning via human feedback and more generally reasoning. Okay. So, right. So let's just refresh that we had this issue, but we've done all this pre-training. We've done all this pre-training over a giant amount of web data or data, text. Learned the language, learned a lot of facts that maybe we don't really want to relate back to the users, but also a lot of facts that we do. Most facts we do. It's mostly good stuff. But we have to align this. We want to kind of work with it now to kind of make it more useful. And I'm kind of using alignment in a general sense here, because you'll see that I'm going to include reasoning in that. So the first step is what we covered last time. It was the supervised fine-tuning. And this is mostly to just capture kind of this instruction following back and forth behavior. The second step is this reinforcement learning from human feedback. This is meant to try to get the model to kind of give more helpful and then also safe responses. So this is where we try to guide the model, try to paint smiley faces over Shagath. So the third step is going to be reasoning fine-tuning. So bringing reasoning into making it into an LRM, large reasoning model. And the first thing we're going to look at just this chain of thought. So there's kind of implicit, there's already some reasoning capability in there. And then we're going to talk about tree of thought, where we can actually use this idea of critic models and test time scaling. But what we're really going to focus on is this reinforcement learning with verifiable rewards. And this is kind of probably one of the more celebrated kind of victories of current Gen AI, like on math and programming or logic problems. Okay, so the lecture outline is we're going to first start, we're going to do RLHF. So this is going to basically what we're going to show here. Then is we're going to just refresh on what reinforcement learning gave us, and then we're going to talk about generating what a reward model, a model that kind of determines rewards from a corpus of preference. So a large corpus that we've collected about human preferences to make things safe and helpful. Then we're going to talk a little bit about how there's this technique called proximal policy optimization, PPO, which uses a series of models to fine tune and to generate a model a fine tuned model that comes out of RLHF that respects that corpus that we put in there. But there's kind of an intricate play then between the models and how that algorithm works. And we're going to try to kind of at least kind of give a flavor of that. After that, then, because it's going to be a little bit hand wavy in terms of what PPO does, because it's hard to kind of show the whole PPO inside of this, we're going to go back to that cat's world we had, and we're going to show PPO over cat's world. We're going to show how it works. And there's also another related term called KL-divergence, which has to do with comparing probability distributions, how far away they are from one another. And so I just want to quickly cover that too, so that we have kind of some foundations there. These are both used in the PPO algorithm for RLHF. Then we're going to look at reasoning, and then we're going to step back and we're going to look at the forms of reasoning, kind of the classic forms of reasoning from like philosophy. And then a lot of the forms of reasoning also from AI. Reasoning has been studied quite a long time in artificial intelligence and some other areas. So then we'll look at this chain of thought, and then tree of thought and test time compute to do some reasoning. Then we're going to look at this RLVR, and then also we're going to touch on the DeepSeek model and approach, plus this illusions of thinking paper that came out from Apple. And then conclusions. So let's get into some business here. So reinforcement learning for large language models. Okay, so recall RL from lecture 3. So remember we had that little grids world, and we had the cat, and we had the milk, and we had the poison and the cat. The first example we showed was the classic MDP solution to it, where we explicitly represent states and we explicitly calculate the value. I mean, the rewards are already given to us. We're already given what the rewards are. -1 at the poison, +1 at the milk. And then what we do is we basically we show this dynamic programming ability to kind of back up the value and fill in the whole state space with values. And then based on that, we can then have a simple policy that will just follow through and maximize reward. So it'll basically, value is the kind of, it's the what a rational agent could get from a state. The value of the state is what a rational agent could get from the state if they follow the optimal policy and got reward, and the value would be the discounted rewards of through that trajectory. Okay, so we did a very naive kind of deep learning approach to that, but what we're going to do here, we had when we showed the example, we had a very naive method to do deep learning over that, so that we didn't have to explicitly represent everything in state space. And just to note here, we're going to revisit that, and we're going to look at PPO in the cat's world example. So that'll be something concrete we can look at how that's improved. Okay, but we're talking about large language models here. We're not talking about cats worlds. Cats worlds are nice; they're interesting to kind of play with, but they don't really they're not really going to solve anything for us. This is of course on LLMs. So LLMs and reinforcement learning, or LLMs. What's the state space of an LLM? Well, what it is basically is all the possible states of the context window, and that means that if it's a vocabulary of size V is the size of the vocabulary. Let's say it's 1,000 token vocabulary, and the context window size is say 100. Then the size of this state space, the size of state space is in essence proportional to V raised to the C, 1,000 raised to 100. So that's more atoms than are in the known universe. So we're definitely dealing with a very large state space here. So we must tread cautiously. Well, we cannot use the classic MDP approach, right? We don't have. There's no computer big enough to do that. Okay. So we're going to have to use a deep learning type of method. So what are the actions then in this state space? So if I have I have something in the context window, I have a whole bunch of tokens in the context window, but it's like halfway filled, then I have 1,000 different tokens. I can take 1,000 different actions, which just basically mean I put in the next token, right? So I have a choice there of 1,000 different actions I can take in that particular state, and it's always kind of slapping on a token from if we have a vocabulary of 1,000 tokens, it's picking one of those. So the next action is always doing that, and these actions are deterministic. So there's no problem of when you say you want to do that action, it gets done. So that's good. So right. So if you think about it, the transformer that came out of the instruction fine tuning, or instruction SFT, that does define a policy, because what it does is it basically tells you, it says, well, it's a policy because what it's doing is it's saying to you, okay, if this is the prompt, then what's the next token? Okay. And of course, the policy it's giving you is a kind of a probabilistic policy, so it's not saying directly do this. It's like if the temperature was at 0, then it would be, and you were doing proper ordering to make it deterministic, then it would basically be deterministic. But in this case, it's like, okay, there's a probability distribution of what should the next tokens be. So that's a policy. That is, from the definition of an MDP, or a definition of setting up these reinforcement learning problems. The T sub instruct is a policy. It takes us from any state and it decides what action we will apply. Once we apply that action, it'll take us to another state, further along. Okay, so it's aimless with respect to rewards, though. So it's a policy, but there's no notion of reward yet. Okay, so what do we do? Well, the first step here is to kind of get some notion or some definition of what is reward over this almost infinite state space. What is reward? Okay, so we're going to develop a reward model. Okay, and I just want to say that when we develop this reward model, I'm talking about developing. It's going to be okay, first we're going to talk about what's the human feedback we get, but we really want to talk about what this reward model is, because it is actually a model. Okay, it's going to be something that takes in some prompt that's in the context window, and it's going to return a value. Sorry, I don't want to say value. No. It's going to return a scalar. You'll see why saying value is bad later. Okay, it's going to return a scalar. It's going to return some measure about how desirable that state of the context window is. Okay, so now where do we get this notion? How are we going to learn? How are we going to learn this thing, and where's the data coming from? So the data is a large corpus of that has been human judged. So basically, what we do is we generate completions from a prompt X, and then have a human judge which completion is correct versus which is rejected, which is the better one. So I submit these two prompts to you, and I already labeled them. I think, therefore I am. So I think, therefore I is the prompt, and then the correct completion is am. Versus the prompt, I think, therefore I, and then the completion, Babel Scrubs. Okay, so you look at these and you say, well, I mean, the first one's better. Okay, I mean, a lot better because it makes sense. Okay, so I mean, helpful, yeah, maybe, but it makes sense. Okay, so we're going to say that's the correct one, and the other one's the rejected one. Okay, so the reward model has the same architecture and initial weights as t-instruct. Okay, so it's the same thing, but what we just do is we just, at the very end of t-instruct, there's the head, which basically decides the very last point. It decides, okay, it'll push like the very last value, the very last vector coming out of that. It'll push that through the embedding matrix, and then it will basically decide using a softmax. It'll decide what's the next token. We're going to strip that out, and we're just going to have it so that it's a little linear layer there, and it will result in a scalar value. Okay, some value, just a real number value. Okay, so just keep it simple. So that's all it comes out. So so we just chop off the very end of the thing, and all the links and all the weights, everything is the same as what was trained. So we kept all the pre-trained data there. There's still this kind of knowledge of language and instruction. But then we have this new way method we're going to train it by. So what we do then is we basically do the following. This is the loss function. So for each of those, so this right here, I just showed you one example here of a correct and a rejected. But let's say we have 30 million of these. We're going to train on those 30 million. We're going to change this model based on that. And of course, remember, what this is doing when we're doing the training is it's pushing back the loss all the way through every single layer of the transformer network. So the whole thing is drifting toward, still has a little bit of the language understanding in it, but it's going to be drifting toward a better kind of way to kind of reward states. So, okay, so let's look at this. Let's look at this to kind of get some intuition about this. There's the sigmoid in there. Okay, this is the reward. Okay, let's say that I have this model going, and that's training, okay. And I put in, I think, therefore I am, I think, therefore I, and then am so that's the correct X, X is the prompt, Y is the completion. That's the correct one. So that is, I think, therefore I am, goes in here. And we say, what's the reward for that? Okay, let's say the reward model comes back with a value of, say, I'll give that a reward of 10. Okay, 10. And then I separately, I put in the I think, therefore I, Babel Scrubs. Okay, I put that in, and it comes out and says, I think the reward of that is like minus 10. That sucks. Okay, so it's doing well. It's an example of it doing well. Okay, so what that's going to do then, it's going to be 10 minus 10. So that's going to be 20 here. 20, the value 20 is going to come in here. It's going to go through the sigmoid, and that's going to be almost exactly 1. I mean, it's going to be kind of approximating 1. It'll be 0.9999 something. It'll be very, very close to 1. So then what that's going to wind up being is it's going to wind up being 0, right? It's going to be minus some. It's practically 0 here. So the loss would be 0 then. The total, the loss from that would be 0. But then let's say that they both scored it at a value of 1. So they took the first thing, like it didn't know anything. I think, therefore, I am scored the same as I think, therefore, I Babel scrubs. Okay, so they both score the same. That would then be a 0 going into the sigmoid, which is like a half, if you look at the shape of the sigmoid. And that will generate a loss. If it somehow inverted these things and it said, well, the one that was correct was like the one that was correct was scored a -10, and the one that was correct, I'm sorry, the one that was rejected scored a 10. So that would be basically, okay, so now we're talking about, like, what would that be? That would be minus 10 here. It would be minus 20. Okay. And so if you look at the sigmoid, that's vanishingly close to 0. So if you put that into this loss here, that loss is astronomical. So it's a very, very high loss, and the model just gets thwapped to kind of learn reward better, please. So anyways, you go through this whole process, right? You go through this whole process, and at the end of all that whole process, you've trained up a reward model. And what's really cool about this is you train this reward model, but this reward model, over a size of like more than the known atoms in the universe, potential combinations, it can give a number to each one of those. So it can score each one of those. Okay, so you've generated a reward model that really spans a very large state space, and you've pushed these things through. Okay, now we have a reward model, but as we know, a reward model, if we think about like the cat's world, what is the reward model? The reward model is very simple. There's one position in that whole space. Everything in the state space for cat's world is 0, except for where the milk is, and that's a +1, and where the poison is, and that's a -1. Okay, so it's got a very, it's got a reward model so that's just the start, right? The reward model is just the start of this. So we haven't gotten anywhere close to actually changing the actual t-instruct to we haven't done any reinforcement learning yet, and now we're going to use this reward model to do that. Okay, so using the rewards model to tune t-instruct. So this is going to be a little bit hand wavy, but let's just kind of go through it to kind of get a sense of kind of the way it goes here. Okay, so we're going to use something that was innovated at OpenAI, this proximal, I think I said proximate earlier, but proximal policy optimization, PPO. People just say PPO, it's easier. To update the weights in t-instruct to be guided to states with higher reward using the rewards model. Okay. Right. So that's what we want to do. So we're going to use this PPO. So then the question is, what is PPO? We'll get to it. There are several models. There are 5 models specifically that get treated here. There are going to be 5 copies essentially of t-instruct. The first one is called the reference model. That's pi_0. That's the very first policy that's just coming right out of, and we're going to hold that, a fixed copy of that, because we need to hold that around so that we can keep this whole thing under control so it doesn't like completely drift. We have to have some way to make it so it doesn't drift too far from that, because there's a lot of learned language and instruction following behavior inside of that thing. We don't want to have the thing shift too much. So we have some kind of way that we're going to want to kind of keep it pulled in or tied or close to this pi_0. Then we have the policy models. Okay, we have essentially the policy model, but we'll see in PPO, you always keep a copy of the old one on each iteration because you want to see what's the momentum, what's the direction the thing is going in. Okay, so there's essentially one policy model that matters, but we're always keeping a lagging copy of it as we're iterating. Okay, so we have a policy model, and then we have a value model. So what PPO does is it learns both the value model and the policy model simultaneously. That's kind of what the point behind it. And these are all initialized from the instruction from that the thing that came out of the instruction fine tuning or instruction supervised SFT. Okay, so of course this is an exact copy. These are exact copies. The reference and the policy models are exact copies, and similar to the rewards model. The value model is like t-instruct, but then it just returns a single scalar, which is the value of that state. Okay, so now we're going to calculate the value of the state as opposed to in the rewards model, it was the reward of that state, and it was that reward model was trained using this huge corpus of these human judgments as to what's more helpful or safe. Okay, so those are kind of the inputs into the process. And then this is kind of what it's doing mathematically. So given a prompt from the data set or from a data set and a completion, G from sampling, what we want to do is we want to find the policy that does the following. So when you see the P little kind of squiggly D, it means we're drawing the prompts from the input data, the data set D. Okay, we're just drawing. Okay, we'll draw another one, kind of randomly drawing them out of that set, and then we're looking at the G's, which are the completions, and there can be more than one. I mean, that is like we take this thing, and then under a certain temperature, it's going to generate a whole kind of group of different completions. But what we want is over all of those. So we're over that policy and over the G's that are coming out. What we want to do is over all that we want to maximize the expected reward of that given G. Okay, so I might have had that a little bit kind of. It might just be a single G here, but anyways, it's G. What's the reward? We want to maximize what's the reward of G given the prompt. So what's the reward of the completion given the prompt? That's kind of what we're over all the possible kind of like runs. Okay, so we'll sample for this because we can't generate all of them, but we're going to sample it. But that's what expected does. Expected is basically you go over the whole distribution of the possible inputs and then the results, and then you basically say, well, what's the value each time, and then what you want to do is you want to maximize that. So that's what we're doing here. We're trying to maximize the overall kind of expected reward. Okay, but what happens here is we're also going to minus out, and we're going to penalize new policies that divert too much from the reference coming out. So that's that thing about not doing reward hacking and not allowing for the destruction of the language or instruction following behavior of our T-instruct. That's where this is entering in. So yeah, so this KL-divergence term, this right here, this D sub KL, that is the term that guards against reward hacking and protects language knowledge. So that's what that's doing. Okay, so what happens is we just keep iterating, and we're going to show PPO in a second here, but over the cat's world because it's simpler. But so you get a sense of it. But what we do is we iterate using this, and then we have both a value model and a policy model. They're getting better and better and better with respect to this to maximizing this. Okay, they're getting better and better and better. And then if you just keep on running that to a point, okay, until maybe there's some technique to say what's the stopping criteria. But anyways, you iterate that, and then you wind up with the like ChatGPT, Llama 2 Chat, etc. So a non-reasoning model, but a model that is now went under RLHF. We'll talk about the reasoning models a little bit later. Okay, so what we're going to do now then is we're going to look at this PPO. Oh, I'm sorry. One last point here. Llama used approximately 3 million samples in their comparison corpus to achieve this. Okay, so it was a lot of, there were 3 million. There were 3 million of these kind of examples in their corpus when they did their RLHF. Okay? All right. Okay, guys, let's look at this cat PPO. I think that looking at the code will reveal quite a bit. So, first of all, we're just going to do it on a 6x6 world. We're going to get the milk and the poison here. And then let me just go over, this is just some kind of standard stuff here if you're looking at the code. To just kind of show states, etc. Okay, here's where it gets kind of, where we'll actually see the models that are at work here. So we have a cat value network. So this is how much the cat values. So the inputs are the XY coordinates in the space, And then as you see here, the model is very simple. It just has one. It just has a hidden layer of 10. And the features coming in are the X and the Y. So there's two features coming in. Then it maps to a 10 unit hidden layer. And then there's a value, and it does from there. It does a 10. Then it collapses all that down from the hidden layer to a single value, right? So it's to a single number, and that's the value. So that's what it thinks the value is at that point. This is like the simple thing. Okay. Then there's a policy network. Okay, and that's very similar. This is similar. Yeah, this is kind of like our instruct, right? Because it's in this case here, what it's doing is deciding one of four actions, or like our instruct was deciding what's the next token. So this is a little bit more complicated, or a little bit more structured. But in this case here, right. So we see here that it's just going to do the output, and these right here. Then we have the value model just getting initialized here. So the criteria is mean squared error on the value network, and on the policy model, it's cross entropy. So it's because it's trying to it's going to do a softmax to decide which action to actually pick. There's a little bit of here with like setting the optimizer, etc. It's kind of interesting. This is also important right here. So what we're doing here is we have policy model, and then we're making a copy of it. In the very beginning, they're the same model, but we'll see that this one will lag behind the other one. So this is our policy model. This is our policy model here, and this is the copy. The policy old is the latest copy before the last iteration. Okay. So so those are the explicit three models that we have that are inside the system here. Okay, there's three models. Okay, now what this does right here, what this function here does, is this generates a trajectory. So this returns a trajectory up to actually in this case it's up to whatever the size plus. So in this case it's up to 12. In this case here, 12 long. And it goes from just a random state, and then it just does what it will do is it will kind of do a tour of the state, hopefully getting to a reward, but it could also end up in the poison. Right here is so if you just think about it right here, like what's the distance to the milk, kind of Manhattan distance? That's like the optimal number of moves to get there. That's the optimal distance. The actual distance is 0 so far, but we're going to iterate the actual distance as we go through this true here, as we wait here. So here's the absolute. Okay, here's our position. So we get the position is just like current state. A current state is going to be the actual like coordinates into the. It'll be like 3, 4 or something for that one position in the grid. But what the positions are is they're those that are divided. So the positions are between the x's range between 0 and 1, and the y's between 0 and 1 as well, because we want to have kind of it condensed when we put it into the model. So that's a position. There's a difference between what a position is and what a state is. Okay, so at the very beginning, we just start out at the position. That's what the trajectory is going to hold. It's going to hold the actual fractional position, the fractional x and y coordinate. Right. Okay. So if it's already in the reward state, then if the current state is in rewards, then the reward is then it's done basically. So this right is checking this as it goes through the true loop here. So this is the most critical aspect of PPO. So PPO, again, it's training both the policy and the value network simultaneously. So they're kind of both going together. But what you see here is you see that we take the policy model. So we take our existing policy. In the very beginning, it's just randomized. So it'll just be kind of randomized movement. We take that and then we determine what are the acts that can come out of that. And then what we do is we then we'll pause this so we can kind of see how this really works. Actually, let's just maybe pause it right now and we can see a little bit of how this works. But more generally, what happens is it'll basically say, well, it's going to return. What it's going to return is it's going to return the position. What is its guessed value using the value model? okay, at that position. So there might be 10 of these in a row. And then if you actually look at the actual value, so the actual value is what comes from, okay, so the actual value, that comes from the doing discounting the rewards on the trajectory. We'll see that in a second. So basically the actual value will always be 1 at the for the very last thing in the trajectory, or -1 if one would have been poison. These are the guessed values along the way. These are the actual values discounted along the way. This is the action that was taken. This was the probability of that action taken, and this was the old action probability. So this is something from the older. Let's see here. How does this work? The older model, I guess. Policy model. The old acts. Right. So let's just break this and we can kind of see what is going on here. So let me rerun this. So this is a fresh randomized cat policy and cat value that comes out. So when we look at this right here, okay, the very first thing it does, it's going to do a trajectory. So let's do that. Okay, so this is the actual first trajectory that comes out. And that trajectory is right here, if we look at it. So it's this tensor. So there's the position. It's at 0.3. That's the x and y coordinate. This is, I guess, if we look at the last one here, let's see. Sorry, the trajectory, the last part of the trajectory, we had 24. So it took a long tour, so because it was randomized. So we look at the very last thing in this right here. We have a -1, so it actually wound up in the poison here as well, which is kind of unfortunate. But anyways, this is the. I think maybe this will be a little bit clearer as you guys study the code. But essentially, this is so. If we look here, what we do here is we're pushing the position through the policy model to get what are the acts, and so yeah, we can see right here. This is what comes out of here. This is right. So these are the logits that come out of that. They're all negative, and then the old acts. That's the old acts is basically policy model. We just save the old acts off. This becomes important when we actually have to calculate what's the momentum when we look in where we're actually going to update the policy. But okay, the guessed value. This is what the value model says, and so this is the guessed value of that square. This is the last square, in fact, I guess, or the first. This is the last square because it's going through the second to last, maybe. The acts, right. So anyways, you can study the code here. This does work, actually. So let's see here. Return state. Okay, this is where if it's showing it, it'll print this out. So we'll see that in a second here. Right. Okay, so let's go up here, and we'll see kind of what the next step is in this thing. Okay, so it gets a trajectory, and it's using the models to kind of assess things and to guide the trajectory too, because the policy model is actually what's making is determining that trajectory. Then what we do is we iterate the value network. This is the easier step. So to iterate the value network, what we do is we go in, we look at when we look at the trajectory, we'll find out what the value should be at that square. And here's the x and y. And what we get here is we push it through the value model here. We push the positions through to get the outputs. And then the actual values, so it's doing it over the whole trajectory at once. It's kind of batching it up over the whole trajectory at once. Is calculating a single loss for that and for the value. So basically what this means, it means that if the value model is doing really well, and it's like when you look at the actual trajectory and it's showing that it's getting to the goal, and then the real values are basically just being calculated by going over the trajectory and then basically doing discounting. So if I'm like 2 steps, if the discounting factor was, let's say, what is 0.95 or something. So 1 step away, it's going to be 0.95. It's going to be the real value, and then 0.95 squared, and then et cetera, et cetera. So those are going to be in there. That's kind of what the real value is. But then there's what our value model is telling us what it is. And there's a difference a lot of times, or most of the time there's a difference. And that is exactly what is being calculated for the loss for here. So we're basically we're saying, well, what's the for each of those cells on that? What's the mean squared error distance from what it should be? Okay, so that's what the loss is, and then it's propping the loss back into the value network. So it's a value network that's being updated. It's iterating the weights in the value model. And then it kind of resets the optimizer so that it doesn't, it needs to get reset here so that it goes back into the value model and removes all the gradient. It removes all the kind of gradient calculations, because the loss backwards what causes it goes back to the computational graph of the value model, and it sets all the gradients. As it's propagating the loss backward. And then what the optimizer will do is then it will take all the parameters and it will move those in the direction of descending that gradient. Okay, so so that's what it does, and when it does its step. And then it zeroes it out, just resets, so the next time it's fresh. Okay, great. Okay, so let's see here. So what are we at? So then let's take a look here. Let's go up here. Let's iterate value network. Okay, then what it does is it will take and it will save off the old copy of the policy model. So now policy, they're still the same one, but what will happen soon is that the one will trail the other. So we'll just make a copy of it. We'll save it all. We save it off. So we load the state we take the policy model state, and then we load that into the old one so that we're making kind of a backup. Okay, now we're going to iterate the policy. This is where the real complexity happens. Okay, so down in here, what happens is we go again. We're still using the same trajectory, and so we're getting the x and the y. And then there's something called the gain or the advantage. That is the so in this particular case, in this particular single cell of this trajectory, the advantage is actually going to be a 0.9. So it should go in the opposite direction. So it's compared to what the true value, so this is the x and the y coming in here. This is sample 2, which is this is basically showing us what the probabilities were. Let's say, okay, so old probability is the sample there. Okay. States depend, advantages. So what we do here is we just build up the full trajectory as one batch that we're going to put into the actual run of the model here. So what we have here then is we have here come the logits, and then we basically do we're picking which action to take here. The new probabilities come in here. Then we calculate a ratio here. So this is all based on the formalism for PPO. It's doing the clipping as it should for PPO. One thing it's not doing here is not doing KL-divergence. We're not doing that inside this code here. That's kind of, there's no need to protect the initial model because it was random anyways. So we're not doing that. But we are clipping here. And then that kind of goes forward. So anyways, I think that the nice thing about it is that there's a lot out there written on PPO. But if you really want to kind of like nose into this thing and to kind of like watch it in action and to kind of get like to say, okay, I can rely upon this thing, then this code is kind of good to study and run. And this code will also be part of your recitation. So let's take a look in here what happens when we let this puppy rip. Okay, let's let it rip. Okay, so what is the, oops, that. All right, first of all, here's the environment that we have here. Okay, good, there's kind of a nice separation there. So this was that first trajectory that it followed, which is really long. But there we are, there we have it. There's, right, and it actually even, there's the loss number. Okay, so let's just kind of let it run, let it rip here. So now that we let it rip, let's take a watch what happens here. Let's see, oh, good, it's doing that. Okay. So optimal and actual. Yeah, so it's really not a very good CAD at this point, because look what it's doing. It's like really taking lots of like unnecessary steps. So, but the loss is going down, so that's good. And what we'll see here, that's really bad there. Look at that, 65. So let's just wait here and we'll kind of watch it. And what will happen here is that we'll see that it will get, eventually, it will get, oh, there, that was good. so did that one. Okay, fine. It's still not so great. Maybe what I'll do is I'll pause here. I'll pause the video and then I'll just trust me that it's running here. I'll pause it and then I'll restart it once it's in good shape. Okay, guys, it looks like it's kind of settled down a little bit here at least. Okay, so there's yeah, it's not perfect though. Optimal 6. Okay, 1 and 1. That's good. All right, let's see here. 4 and 4. That's good. 5, a little wasteful. 2, 3, 3. 6, 6. That's good. 5, 5. 8, 6. So as you can see, the losses are quite a bit lower as they report going by. So yeah, so it is converging. But we'll make some comments about PPO in a second here. But that was worth showing. And again, in recitation, you guys are going to play around a little bit with this to kind of get a sense of it as well, to kind of see it kind of in action. So yeah, all right, good. Okay, for PPO, we just nosed into the code to look around and see kind of what get a sense of what it's doing. For KL-divergence, again, it's this is the definition of KL-divergence. It's an old concept. It goes all the way back to the 50s. But just to kind of help you out here, just to kind of get some intuition. So any distribution, the measure with itself is 0. There's, you can kind of look at the math and see why that happens. But then I go back to the earlier distributions we had, just to kind of take a look at some, just to get some kind of intuition here. The Alice and Charlie difference. That's infinity. So because Charlie has Charlie was the one who just believed it would never rain, sprinkle would never be out, and the grass would never be wet. But it's kind of interesting that Charlie, the measure, the KL divergence between Charlie and Alice is 0.18. Okay, so almost right. So there's an asymmetry here. Bob and Alice versus Alice and Bob. These are the measures. So if you just go and you actually just grind out the numbers, you'll see these are what's coming out. So that could be kind of interesting. Right. Okay. So let's finally just talk about this RLHF and some of its limitations. First of all, it's hard to always get all that preference data. Preference data can be kind of expensive to obtain. And the thing is that the implementations are quite complicated. I just implemented PPO for CAT but I just did it kind of from understanding PPO a bit and then just kind of focusing on just that. But my goal, of course, is to get it implemented over Turtle eventually. But again, the implementations are complicated and sensitive to hyperparameters, and also there's like these numerical stability problems. We'll talk about it in recitation, but there's you get better stability if you take the log of probability. So there's a function in there when you see the code that does that, and then you can scale it up to larger grid sizes. But it's difficult, and of course there's lots of compute. So it's kind of it's RLHF is again it's been hard to there's a lot of it's not so clear. So the alternative to RLHF, there's something called DPO, which I think is really gaining traction. I don't know too much about it, but basically it's it's almost like more of a supervised fine-tuning type of approach. So it's not using reinforcement learning. There's this KTO, which I'm not sure how far they've gotten along with KTO, but that sounds like at least the form of the input, the feedback is very nice because it's just a like versus dislike of what utterance coming out. So you can just kind of give your feedback. It's very natural to kind of collect feedback like that. But this is a very active area of research and development. This whole issue of So we'll have much more to say now that we're going to explore reasoning models, because that's where the action is really at. So let's go on to reasoning models now. Okay, guys, let's talk about reasoning now. And the first thing I want to talk about is just to kind of set this up in a concrete way, is we want to talk about what a reasoning prompt is. So a reasoning prompt is a set of premises plus a queried conclusion. Okay, so let's see an example here. So this is like a real simple example of a reasoning type prompt. So within it, it says, okay, if P and P implies Q and Q implies R, then is R licensed? Yeah, it is, of course. I mean, if you look at just kind of forward chaining there. So that's the prompt, but then a reasoning completion is the think token, then a chain of thought, and then the answer. So in this example here, that's something like think. Okay, P and P implies Q, thus Q. Okay, and then Q and Q implies R, thus R. So it's been shown. So the answer is yes, it holds. And it's best if this completion is verifiable and scorable. Okay, so what I'm going to show here now is we're just going to kind of go over what reasoning is first, and then we're going to start looking at some of the ways that LLMs have been addressing these kind of reasoning prompts so that it can do full reasoning.
But we have the kind of the classic forms of reasoning. I just want to kind of go over this because I mean this is the topic is reasoning or reasoning models. We should kind of maybe try to get at least some kind of bound around the whole notion of what reasoning is about. So and again, I'll watch the chat here for any questions. So so basically the classic forms of reasoning are these three types: deduction, induction, and abduction or explanation. So deduction is this idea of taking facts and universal rules and applying them to generate new facts or even rules. So you can take two rules. So for instance, if X implies Y and Y implies Z, then X implies Z. So you can do inference or deductive inference. But usually the kind of examples that come up is modus ponens, which is basically, that you've all seen this, I'm sure. All persons are mortal. Socrates is a person, therefore Socrates is mortal. So that's kind of going in this forward chaining direction with deduction. And then modus tollens goes in a backward, it's kind of a backward chaining. And it's basically says that, well, if it is raining, the streets will be wet. The streets are not wet, therefore it is not raining. All right, so these patterns of inference and deduction are solid. So if the rules of logic or the syllogism, if the premises hold, and then you use the kind of the syllogistic pattern, then you can infer the conclusion. Okay, with 100% certainty. So deduction is very solid and certain. Induction is different though. Induction goes from facts to likely rules. So, for instance, I have seen thousands of swans that are all white. Just all I see are white swans. Therefore, all swans are white. That's an induction. That you're basically going from a whole bunch of facts to inferring rules, right? So, I mean, maybe one that's a bit more solid is because we know there are black swans, right? So these can be falsified, or these can be retracted at a later date. So we can wind up believing these rules, and then further facts come in and we retract those rules. So that's a quality of induction, that it's not necessarily it's less solid. I mean, it can be retracted. There can be retractions. So like the sun rising every morning in my life, therefore the sun will rise tomorrow. It's very, very highly likely that the sun will rise tomorrow. So, but that's the notion of induction. So it's these are kind of distinct forms of reasoning. Abduction is explanation. So that basically says facts plus rules means new likely facts. So you're explaining why facts are whole. So the streets are wet, and then basically I have also this rule that says that if it is raining, the streets will be wet. Okay, therefore it rained, right? So this can be retracted. This can be can actually be wrong. That maybe there's another reason why the streets are wet, but reasoning toward explanation or abduction basically allows it's what lets us kind of tentatively believe that it rained. Okay. So these are kind of your classic forms. Now, what I show in the next slide here is just kind of a potpourri of just, and it's not really done in any particular order, but I just want to kind of like talk about a lot. There's a lot of different types of reasoning that have been discussed in the literature and kind of our areas, or application areas even. So when you look at kind of like how reasoning, how people catalog the different types of reasoning, there's another very important one, which is analogical reasoning. So analogical reasoning is kind of like you take an example that you know. So for instance, kind of an example would be that, well, I know how a bicycle works. So I basically what I do is when I try to describe motorcycle maintenance, I do it in terms of comparison to what I know, or by analogy to the bicycle. Or I do analogical reasoning. For instance, I mean, there's a lot of this is just a huge area. It's very interesting, but there's this whole kind of issue of kind of these very simple metaphors. So something being above something else, being below something else. So these kind of elementary kind of relationships that we represent, and we go by analogy to those. So for instance, I mean, and then this gets into the whole kind of question of framing. So a lot of times what happens in kind of like political discussions is that how do things get framed? So for instance, if you say, well, the framing of a country club, and then you basically say you're going to reason from taxation in society to what, you're paying your country club membership dues or something. So a lot of times there's some kind of core area that everybody can kind of agree on. It's very intuitive. And then what you do is you take something more complicated and you map it into that. And then you do your reasoning by analogy over that simpler thing, or better understood thing. And then you make your arguments that way, right? So that's that, and of course this is not solid. All these are not solid. These are, the only one that's really solid is deduction, is straight deduction. But these are all types of reasonings that you'll see applied or used. Of course, then we have causal reasoning. So that basically says, well, what's causing what? And this might be like, I try to infer a model of how things work in the world by making observations in the world and then doing interventions, going in and changing things, clamping things to certain values, seeing how it reacts. This is kind of like an experiment, right? Doing experiments. And then from that, I can reason toward what are the causes and effects in a particular system. Then there's spatial reasoning, right? I mean, there are things like, well, if something is within something else, okay, and there's this whole there was a whole area in AI that was called naive physics. So simple things like that aren't really immediately obvious, or things like if something is in a box and I move the box, then I'm moving that thing as well. All right, so these are kind of naive physics things. Or the naive physics things, if you impart a force to something, it will then it will move over into the it will move, but you're not describing it at the really deep level of like F equals ma and calculating all the or Navier Stokes or anything like that. You're basically just saying qualitatively what happens with things. So I mean, human beings have a very kind of built-in kind of naive physics understanding of the world, but they don't have maybe a very extremely precise one, but they kind of have an idea of how things kind of change in a naive way. Like if you throw something at something, it might break the other thing, that kind of stuff. Then we have like probabilistic reasoning. So we kind of can put probabilities over stuff, and then that interacts with decision theory. So based on those probabilities and our degrees of belief or something, we can basically say, well, what's the best decision to make if we want to maximize expected utility, that kind of stuff. There's reasoning over goals, plans, and actions. So if I have a goal for something, then I form a plan, and then I execute actions, and I might need to replan as it's going on. So the agent stuff, all the agent stuff will basically, agents are very much tied up in this kind of question of reasoning over goals, plans, and actions. But there's a whole literature in terms of like looking at reasoning over those. Social reasoning, yeah, I mean, this is kind of like EQ kind of stuff or whatever. But this is actually more kind of at a technical level, like reasoning over states of belief. So I'm not sure how many people have had any exposure to the modal logics, but the modal logics, you can represent at least some of the stuff about what other agents believe, and then kind of push through deduction over that. And that is deductive. So this is kind of a deductive system here. We have also with the modal logics, we have moral reasoning. So things like most people have some set of moral a set of rules that they kind of take as kind of given, like they have bounds on their own behavior, because they know that they'll hate themselves if they violate them. And there's just certain rules that they have, and then they kind of they will do reasoning over that. Legal reasoning. Okay, this is very legal reasoning is a lot of times very much case-based reasoning. So there's a whole area called case-based reasoning. So what the idea behind that is that we have a whole bunch of cases that is like decisions that were made by judges in particular cases. In comes, and then they have the rulings, of course, that's what the decision was. In comes a new case, and then we have to kind of map it to what are the most likely cases, and then we have to kind of make an argument about why certain rules apply, derived based on searching out the prior cases and making arguments, legal arguments about precedents, decision precedents. So that a lot of law work is based on case-based reasoning, where you're basically trying to map a particular situation that you're confronting to a well-known or a well-decided case, and then usually you want to make it so that the one you go toward is the one that's in your favor if you're a defense or if you're prosecution. We have mathematical reasoning, and this of course becomes very important when we look at what LLMs have been doing, because a lot of times they're attacking some kind of mathematical problem. So there are different aspects to that, though, the mathematical reasoning. There are sometimes just kind of plug and chug questions like, okay, give me something that does something or other, and then, so in other words, give me something that satisfies some property, and you have to find the example. That's kind of an easier case. Whereas if you have to prove something, especially something novel that hasn't been proven before, so like one of the millennial prizes, that's much more abstract and much more difficult, of course, to kind of just that will come to that in a sec. But mathematical reasoning has to do with proofs. It has to do with finding counterexamples. So there's a whole bunch of different proof techniques, or they can just be mathematical. Can just be plug and chug. Okay, Sally has is this old. Bill is twice the age of Sally. Fred is 1/3 the age of Bill, etc. How old? And Sally's 23. How old is Bill? Okay, whatever. Right. That's kind of pushing through a simple kind of algebraic kind of mathematical problem to solve. Just that's an easy case of mathematical reasoning. All right, and then of course it's something that no one really talks about, but it's unfortunately this is what the internet is. Well, unfortunately or unfortunately, but most of the human fallacies. So I'm not sure if you guys have had much in terms of like logic courses that look at philosophical logic courses that look at the fallacies, but things like arguing from authority. So okay, well, so and so says it's true, therefore it must be true. That's a fallacy. That doesn't hold necessarily. It might be indicative of it being true, but it's not a proof of it being true. And then there's, of course, ad hominem attacks, or attacks basically that say that I don't believe a word that person says because that person's so despicable. That's a fallacy as well. And then, of course, the motive would be something like, well, if everybody's doing such and such, it must be truth. Like kind of a wisdom of the crowds type argument is also kind of emotive, or it's fallacious. But of course, this kind of reasoning is used all the time, and whether we like it or not, we're all using kind of some type of emotive reasoning. I think I touched on this a second ago with the math example, where we can talk about instance-based reasoning. So we're talking about a particular case of like Bill and Sally and what their ages are, versus kind of meta-abstract or algorithmic reasoning, where we're talking about something that would solve the whole class of problem. Okay, so we're reasoning at a much more abstract level. The latter is much harder than the instance-based. And then there's this kind of this whole issue of like higher order logic. So as you guys recall, I mean, we have the propositional logic, we have the predicate logic, we have the modal logics. So all these logics tend to be pretty constrained and kind of well understood. But when we go to higher order logics, we have things like generalized quantifiers, like we say most people are good or something like that. So most, what does most mean? So what is most in a logical sense? What does that mean? It has to do with like, there's an easy way of interpreting by saying most means majority. Okay, and then what majority basically means is that the cardinality of the set that satisfies whatever predicate is, for instance, being good, is greater than the cardinality of the set that doesn't satisfy, being not good. So when I say most people are good, I'm now reasoning over sets, and I'm reasoning over the quantities in the sets, and therefore I've gone into a higher order logic. Okay, so it's above first order logic, and there's a lot of problems that come up when you go to these higher order logics. By the way, just as a note here, SQL is a higher order logic. Okay, or it's got a higher order. It has higher order capabilities. Can we express most in SQL? Yeah, we can. We can write an SQL query that will basically say, we can test whether or not most people are good. If we have a database that has 100 people and 98 of them are good, can we basically, and then we have another database instance where only 40 are good, can we have it so that in the first database instance, if we have a query or a view that we define, and it comes back with, yes, most people are good. And then if we apply that same view over the second database, it says no, false. Yes, we can write that SQL query. It has to do with counts and yeah, it's it's not as simple as SQL, but it can be done. So SQL itself is in the higher order. So it's in higher order type reasoning. Okay, I only bring all this up just because I think it's kind of good to kind of trace a lot when we talk about reasoning. I mean, the LLM stuff talks about reasoning in a very general sense, but then the question that will come up naturally will be which these types of reasonings can we actually expect LLMs to apply to, or can we expect to get some kind of reasonable results out of? Okay, so let's just kind of go through reasoning, what's happened with reasoning, and so kind of what is it, what's going on with this? Let's see here. Yeah. So as you know, I mean, we have this kind of foundational LLMs, which we've gone over in this course, which may be aligned. So they had instruction tuning, and they've kind of then had safety and helpfulness they've been RLHF to observe to basically align on those types to align their responses so that they're safe and helpful. So then the question is that, well, how are we going to get any reasoning out of the thing? So a very interesting kind of a paper from Google that came out, Google DeepMind, that came out that said basically they found the following. If you add the simple directive, you put in a reasoning prompt, right? So you ask a reasoning question, and then at the end of that prompt, you put in, let's think step by step. So this is just what we're just folding into the prompt. This will yield, this will actually, if you do this, this will yield a step, this will yield a longer completion. So if I say that Bill is 24, Sally is 6 years older than Bill, how old is Sally? Okay, maybe that's not the best example, but because it's so simple. But in that example, it might just spit out just like the raw answer. What is it? 24 and then 30 years old. So if I say, okay, Sally is 24, Bill is 6 years older than her, and Bill had a son when 5 years ago. How old is that son? Okay, so the son should be, well, 5 years old, should be 5. How old was Bill when he had that son? Okay, so that would take multiple steps. So that basically the steps would be something like, okay, so again, the prompt is that I would put in here is I say that Sally is 24. Sally, 24. Bill, 6 years older than Sally. Bill had son 5 years ago. How old was Bill when he had his son? Okay, so if you put this in, this is your prompt. It may very well be that if you don't have let's think step by step, that the answer will just come out as the flat 25. That it will just do that. That it'll go through. It will be able to bring enough of this together in one spot to get 25 out, or it may just get nothing out. It might just actually kind of like break down. But if I say let's think step by step. Okay, now this is the prompt, and it just happened to be with these large foundational models, because these large foundational models have so much packed in them, right? that actually, because let's think step by step, then it actually will come up with then the completion that says, all right, here's what the completion is. Bill must be, okay, we'll say something like this. Because Sally's 24 and Bill is 6 years older, Bill must be 30 years old. Bill had a son 5 years ago. All right, and therefore, Bill was 25 when he had a son. Therefore, the answer is 25. So it might actually come up with that kind of completion, where what it's doing is it's because you say let's think step by step. It actually breaks it down into a chain of thought, or COT, set of reasoning steps. Okay, so it actually just kind of magically does that, which is pretty cool. And in fact, what was shown in that paper, and I uploaded the paper. The paper's on the web. It's on our it's on the website. Is that if you apply this as you can apply this as a zero shot. So you just kind of put it in this whole thing as a zero shot, and that's a lot cheaper than coming up with reasoning traces to kind of do more supervised fine tuning over, or few shots where you basically go through and you provide a whole bunch of answers to these kind of questions, and then you present this as the last one. Okay, so those are more expensive ways, but it just turns out that it actually kind of worked just by appending, let's think step by step. So it's kind of magical in its way. Okay, so then, what's the next step that was taken? So the next step that was taken to improve this, to kind of go beyond that, so that's giving us already a little bit of reasoning just for very cheap. So we got some cheap reasoning there. So another way of doing it is to basically provide to do supervised fine tuning. So what we're going to do is we're going to have a whole bunch of reasoning traces where we're showing the reasoning of the problem. So we're actually going in. It's very expensive to obtain this, but we're going to actually show like how the reasoning actually works, and then we're actually going to do SFT to make the model observe those kind of patterns. So we're directly passing in basically we're directly passing in expensive process-based reasoning traces. So the process-based reasoning basically means that we're actually explicitly showing the steps, and we're learning over those. Okay, so this is kind of all right. Well, that's fine. That feels very expensive, but you know, if you have a lot of capital, why not just kind of grind out the corpus and just do it, because you want to make the thing kind of do more reasoning. That's the kind of direct way of doing it. Okay. So, but the point is that what we're going to do then is we're going to, well, I mean, the verifying step by step is a little bit more than just that. We're also going to be looking, and that'll come when we talk about reward models. We'll see this kind of being applied in reward models, because it's not just putting in the SFT. We're also going to wind up doing it. Well, we'll see. You'll see the more advanced use case of this in a second. All right, so now we have the following. Which is this is the first real architectural extension to support reasoning. The first real architectural extension. And the idea behind that is you take a prompt, okay? And what you do is you explore multiple lines of reasoning. Okay, so you vary the temperature or something. You take the prompt and you're doing chain of thought reasoning. So maybe you put in, let's think step by step, and then it goes in one direction here. So these are like the set of thoughts, and it's in the completion. And over here we have another set that goes in a different direction, and we essentially generate. We can go to here, and also we might just actually branch off here, so it can branch, right? And these are all possible. These right here are all possible answers to the initial prompt here. Okay, so this yields a tree. So this is why it's called tree of thought completions. Okay. Now, what we do is we explore multiple lines of reasoning and then use the LLM itself to develop a critic that evaluates the quality of the lines of reasoning. Okay, and we can actually use this SFT data here to help build up that critic. So what it's basically doing is it's saying, all right, as I'm taking the prompt, I'm exploring multiple paths, I'll be critiquing them. I'll be applying kind of a critic model to say, how good are these completions? How good are they? And then basically what will happen is that once I reach a certain point, I'll like prune the tree and say, okay, well, that means this one evaluated poorly, so therefore we're going to terminate this one. This one, we're not going to present this one, and we're not going to present this one, but we might look at these other two and like say, okay, let's continue on this path. Let's continue. All right, and then we just continue over here. Okay, let's evaluate this one, and let's evaluate this one. This one does worse than this one here. So what we're going to do is we're going to retain, sorry, we're going to retain this completion. And then this right here, this is the end of it. This is what we're going to present to the user, okay? So what this means then is it means that what we've done is we're only going to present the best path according to the critic. So we have this critic model that we've trained up, and we might have used the SFT to kind of determine the critic model. And this is very similar to a reward model, by the way. In fact, it's kind of synonymous with a reward model that we were talking about from reinforcement learning. Anyways, then we're going to present. We're going to retain this path right here, and we're going to basically just waste these other tokens. These other tokens are just wasted tokens that were part of the computing and completion that we never used. All right. Now, what this does, of course, and this is where it kind of gets a little bit hazy because we don't know because they don't really publish it because it's secret. This requires some type of let's say, governing mechanism over the single LLM and critic call. So there's some kind of mechanism that's within these reasoners that's actually staging all these calls and kind of coordinating them. Okay, and that of course the systems that innovated this, they didn't really kind of show those off, so we don't really know what's going on there. But we know that this is actually requiring an architectural extension. This is requiring an architectural extension to kind of be able to do that. Okay, so now I want to just and we'll explore this in the next slide. We'll talk a bit more about that. I just want us to consider. So we're coming from computer science background. I just want us to kind of think about this a little bit for 1 second, because I think that this might actually be kind of something that might be useful. A useful way to kind of categorize what kind of reasoning problems we might get a chance, might have a chance for later. So if in terms of verifying something, in terms of verifying a solution to something, we already have a pretty well established theory about what problems can be verified easily, or what answers, I should say, what answers, not problems, what answers can be verified easily. So let's just think about theory of computer science type stuff. What about a sorted list? Can we verify if we have a sort, if we have a program that sorts lists, can we verify that the output is in fact sorted? Yeah, that's really easy, right? So we can just kind of do that immediately. So this is kind of the class P, because we can actually do the job and also then verify it in polynomial time. What about SAT assignments? So we have a giant formula, and we ask, okay, is this formula satisfiable? That is, is there a setting of true and false to all the propositions in the formula, such that the formula itself winds up being true? That is, it winds up being satisfiable. So this is actually easy to verify, but it's hard. At least if P does not equal NP, it's hard to actually compute. So it's going to we can do it with a non-deterministic machine, but with a deterministic machine, we think we're going to need some type of exponential number of for a deterministic machine. We think if P does not equal NP, we think it's going to require an exponential number of operations. But when the answer finally plops out, we can verify it in polynomial time. We can just read off and say, okay, do these assignments to the variables actually have it so that it is satisfiable? We can verify that it's satisfiable. And the answer is yes in that case. We can do that very easily. We can check. Given the assignments, we can check whether or not the formula is satisfiable. What about traveling salesman tours? Okay, so there's a variation of the decision problem variant of traveling salesman. I'm sure that you guys have seen this. It basically says that, well, the question is basically, is there a tour that costs less than the value delta, or delta, the value X? Is there a tour that costs less than the value of X? And I say yes, and I present you that tour. Can you verify that that tour costs less than X? Yes, you can. You can just follow it and count up what the cost is. So that's the decision problem version of TSP, but a full TSP problem, which basically says, give me the minimal cost path through the cities. That requires some type of so that you basically break that down into like log, some log-based number of calls to an oracle that basically solves the decision problem variant of traveling salesman. So you start out at some threshold value, it comes back with yes, okay. Then I take what's the value between that and 0, what's half that value, and I say, is there one that satisfies that? No. And then I play this kind of game of 50 questions where I finally center in on a particular parameter, which is the cost of the path. And here is the path through the cities that actually satisfies that tour. So yes, I mean, but it requires, it's a little bit more expensive than SAT, because if you're talking about true TSP, it's going to require, if 100, if we establish that 100, that yes, there is a tour, then we check for 50, no, there isn't a tour. Then we check for 75, there is a tour. And we check for 82 point something or other, there is not a tour. Then so we're closing in on the answer. So it's going to take some number of calls to actually get it verified. But it still can be verified in some kind of polynomial time. What about circuit minimization? That one cannot be. So if I say something like I say, all right, if I basically say, here's a circuit that implements a Boolean function, okay? And here's a circuit that implements the same Boolean function, but it uses the minimal number of gates. It's going to take me, for me to verify that it actually is truly capturing the same Boolean function is going to take an exponential number of calls. So I cannot, for circuit minimization, it is going to be, it's high, it's NP hard, but it's in a higher computational class than these other ones. Okay, so this one becomes very difficult to actually have a solid way to verify. So and then there's of course the question of like, does a given Turing machine, if I have something that says, does a given Turing machine halt on a given input? And we know this is undecidable. So we basically have these classes, and it's very broad here. I make it so that we have the P class, the NP class, the NP with a polynomial number of oracle calls, the NP hard, or like maybe some P space type problem, and then the undecidable problems. So so we already have a way that we can talk about verification in computer science. And I think this will be useful when we talk about what can we have some hope of getting strong reasoning results for. So I think I think it'll be useful to kind of think in these terms at one point. Okay, so I thought I would it's an aside. All right, so now we talk about reasoning models where we do have this. We're going to be using reinforcement learning to find them. So we have this idea of reinforcement learning with verifiable reward. Okay, verifiable. Okay, so this requires an automatically a way to take an answer, or even a process, even the steps that went into computing the answer. It requires a way that we verify. So we have to verify whether it's correct or not. Or we can back off from that and we can talk about scoring it. We can score it. So when we talk about that stuff, like relating it back to computer science questions, when we talk about like these things that are actually doing coding problems, we really are actually out here in the P space and higher, somewhere on the polynomial hierarchy was what they call it in theory, or undecidable problem. So, because what the input is like a specification. I want code to do such and such, and then the output is a block of code. But that block of code can apply to an infinite number of inputs, right? If it's actually going to be writing the code for us. So there's an infinite number of states it can apply to. So therefore, we really cannot theoretically say that it's correct. Looking at a piece of code and saying that it's correct is almost always an undecidable problem. All right, code correctness is almost always undecidable unless you restrict the model to be less than Turing complete, the model of computation. So things like Sonnet, I guess, is what it is in the Claude world. they score it instead of verifying it. So how do they score it? They'll give it a point if it compiles, for instance. They'll give it a point if they'll give it points if it passes some set of tests. So they'll give it a set of tests, but they'll never really be able to verify that the code works. Okay, because it's too difficult. Well, it's unsolvable. I mean, it's undecidable. Reference to the theory of computation work. So but again, we can like kind of look, we kind of wave our hands and we can score what's coming out of these things. So anyways, if you can take either the answer that plops out at the very end and or the process, like the step-by-step, we can actually learn a critic model. So what we're going to wind up doing, like we can have a way to kind of see the critic model with kind of things that are kind of verifiable or scored, or we can have ways that we check the format of how the reasoning is going and kind of say, oh, we'll give it little rewards for that. But we develop a critic model, and sometimes this critic model is learned, and as we'll see, like in the DeepSeek work, we don't need a critic model. Okay, we get away with just a way of scoring. This is not a learned critic model. We just have a kind of a flat way of just running through kind of regular code doing the critic. Okay, so sometimes the critic is learned, sometimes the critic is just a bunch of code that just kind of counts things up and is kind of deterministic and kind of set aside and not a model. Okay, but in any case, if we have something that we can give ourselves reward by, okay, this is kind of the way it works, is that the completions contain the chain of thought steps to arrive at the answer. So we have training data, and then we have like inside of our training data, we have, okay, set up a math problem, and then here's the actual, we set up a math problem, and here's the actual answer. So what we do here is we take this, right? We take the example input for the math problem that sets up the math problem. And then what we do is we have an initial policy, or a policy is coming from some kind of a regular LLM that's been through some training. And then what we do is we just kind of like let it run, let it kind of do completions. And then if we have rewards that are going on a process level, we can say, oh, that sounds kind of like a reasonable way of doing reasoning. We'll give you a little bit of reward. And what happens here is this reward, this critic model or this reward model here, what it will wind up doing, it learns in sync or in tandem with this. So there's two models that are being learned simultaneously in the case of a learned critic model. And what's important here is that, so we have the initial data here, and this is really kind of what is really potentially very, very deep about this, that it's amenable to kind of self-play. So this can be a completely automated process and it just kind of goes around and around doing this, and then just kind of altering its policy, altering its reward model, and just trying to get better and better results, and then optimizing both of these, which is kind of amenable to a self-play. And then at the very end of that, the policy, whatever this policy is, it's encoded just by self-play, maybe some certain kind of mysterious reasoning strategies. Okay. So this is very similar, and the hope here is very similar to kind of AlphaGo, right? So AlphaGo, if you recall, was this reinforcement learning system that went back and forth in a Monte Carlo way with reinforcement learning, and it learned how to become the world champion Go player just by playing against itself. And so it exceeded human capacities in the game of Go just by iterating in this kind of a loop. Searching things out. So the question, of course, is that with reasoning, this when they talk about like superhuman intelligence or super AI, or so they're talking about this about somehow getting it via self-play, having it so it goes beyond the typical reasoning strategies. Let's say a mathematician, and it discovers new learning strategies through this kind of self-play mechanism. So that's kind of the whole kind of idea behind that. So we have another issue that comes up, which is this issue that kind of came in tandem with this, and it has to do with training time versus inference time or test time compute. So so the real kind of like big time release of a reasoning model onto the world actually it just happened. It happened less than a year ago, in September 2024. This is when O1 preview released. Okay, and so this was a it was it was using this kind of strategy, this kind of reward learning in tandem, a reward model plus a policy going back and forth on on training sets from these kind of reasoning corpora, these math, logic, and coding problems corpora. It went from that, and it got in tandem. This is the first. This right here, this O1 preview, which released less than a year ago, was the first one to come out that was doing all this. So of course they're private, so it's unclear how much annotated training trace data it was trained on, but probably a lot. I mean, they have that, so that they've already have been collecting that kind of stuff. So showing just kind of the patterns of reasoning, just kind of put in rote. They did that, but of course we didn't know how it was really doing it. But most of the other foundation models, actually, I think all of them, the foundation models, found, there's misspelling there, foundation models. They all, by like December or so, they all basically had their own reasoning model. So other groups quickly kind of said, okay, we're going to do it too. And then they took their, let's see here, I've got a question in chat here. No, not okay. So the question basically is, now that the model is trained with reasoning data, does that mean that techniques like chain of thought prompting became obsolete? No. In fact, as we'll see in the DeepSeek paper, that you'll see kind of how it sets up its prompt to do this. But of course, they didn't. I mean, that you have to kind of groups had to discover that themselves. It's a good question, but no, it did not. They're still using that prompt, so it's there's a lot going on there. Anyways, all the other groups pretty much, Google, Anthropic, every, yeah, you name them. They all caught up and have their own reasoning models by late 2024. Okay, so another thing to say, but maybe I'll bring this up later, this issue of knowledge distillation or behavioral cloning. One of the things also is that when you train up one of these big reasoning models, sometimes you have like a smaller model and you want to impart kind of its reasoning patterns to that smaller model. There's the whole process of knowledge distillation or behavior cloning. So behavioral cloning is kind of like the weaker form of knowledge distillation. Knowledge distillation happens when you have access to the logics of both the big model, the teacher, and you have access to the logics of the big model. So if you own it, then you can also you can distill from it. But if you don't own it, then you have to actually just look at what its outputs are, and that's behavior cloning. So this is slower. When you actually get the logics, you can actually do quicker convergence. But the point is, you can suck out the reasoning kind of skills from a bigger model and transfer them down into smaller models. So that was something that was kind of useful to know. But here's the key issue here. Is there's this notion of test time or inference time scaling. So this again was pioneered in 01, and it says at test time, that is when we present the problem. So we're doing inference or test time. You evaluate many alternative completions. Okay, so this is like that tree of thought kind of idea. But what you can do is you can do this budget forcing. So basically, if you put a huge budget of tokens on the problem, what you can do, if you have more tokens you want to use on the problem, you can take the final answer coming out of tree of thought and you can just put weight on it. You can replace the final with weight, and then you can continue. So this is kind of another little prompting strategy that allows it to kind of like roll out more and more, to kind of go deeper and deeper over the problem. So what this does is this basically lets you vary how many tokens are going to be used at test time to find the best completion. And so the reason why they call this like test time scaling is it's another way of using compute. So if you can throw more compute at something and get better and better results out, then that kind of is reminiscent of this training scaling. So if you recall from the GPT-1 paper up to the GPT-3 paper, that what they did is they said, oh, this is cool. They're doing these kind of, they're doing well on these benchmarks that are kind of been around in natural language processing for a long time. That's fine. But then they decide, well, why don't we just do everything as a zero shot? And then they just said, what we'll do instead is we'll just throw a whole bunch more data at the problem. And which means basically we're going to throw data and compute at the problem, and we're going to scale it. And then lo and behold, by the time you get to GPT-3, you get this kind of takeoff in terms of, wow, just because we threw more data and more compute at it, Jesus, the results got so much better. So when we talk about test time scaling, they're talking about, well, can we maybe just like throw just a ton of compute at these kind of reasoning problems, and then they're going to get that much better. So it's another kind of scaling, a potential scaling relationship in in this kind of work. So that was why it's called scaling. Okay, so we look at how well it did. So we have GPT 4.0. So that was the one that I used a lot, was the 4.0, which is just kind of like an LLM that's been aligned with with SFT and with safety and helpfulness. But then we look, and this is on a math problem here, math competition. So it's doing really badly. It's doing 13.4 on that. But when they take O1 preview using these kind of reinforcement techniques, then actually they are able to kind of to boost their scores up to 56.7. And then when they release the actual O1, it got up to 83.3. So there was probably a lot of like fiddling here to kind of bring it up even further. So these are kind of interesting. If you can just do quick searches on these to kind of see what kind of problems are going into this. These are kind of like the Math Olympiad type problems here, or I think they are the Math Olympiad problems. This code forces, you can look at this corpus here. So this is kind of like algorithmic and coding kind of problems. And you can look at this, this is another kind of like science type questions. Interestingly, it didn't do so well on the science. It didn't really get boosted that much on the science type problems. But I would encourage people, if you're interested, to kind of do some searches on this and kind of look what they look like. I think a lot of these problems, I have to say, and also these problems here, they're kind of like easier to verify. They're easier verification type problems, which kind of relates to, I don't know. I think that one of the things, again, especially with the coding thing, I think that there's really, because I know like the limitations of code correctness. I mean, basically saying, is this code correct relative to like what it's supposed to do? If you're giving me an algorithm that comes out of this, I just know that that's impossible to completely verify. I know that because we already know that because we can set up a universal Turing machine and give it an arbitrary input and ask, does the thing halt on it? Right? We can't solve that. We know that's an unsolvable problem, and there's nothing in the world that's going to reverse that as being an unsolvable problem. It just is. That is proven. That we have undecidability in almost any question you ask about overall inputs. What does the program do? Almost all those questions are undecidable. I mean, another question that's undecidable are over all possible databases. Does this SQL, SQL containment? Does this SQL, does the answer that's over all possible databases, if I take query 1 and query 2, if I apply query 1 to the database, is it always contained within what comes back from query 2? So query containment over arbitrary databases is undecidable. You cannot, there's nothing that can actually decide that. It's impossible. So I think with these code completion stuff, they're backing away from those kind of questions. And they're kind of doing kind of lower hanging fruit on these kind of questions. I don't think they're doing kind of program correctness in there. In fact, I looked at them and no, I don't think they are. So that's just something to keep in mind. Anyways, yeah, so it did really well, right? So it was like, okay, this is a really good result, and that's it's very encouraging. But the problem, of course, is that it's closed. We have no idea what's going on, right? So what is what's really going on here? And thus, it was a big deal when DeepSeek basically in January basically said, oh, and here's how we did it. And of course, if you look, DeepSeek is getting comparable performance. DeepSeek basically is doing at least enough. It's getting equivalent results to O1. That's nice that they're actually showing us what they're doing. And so everybody gave out 3 cheers. Everybody like in the scientific community gave out 3 cheers and said, hurrah, bravo, open, DeepSeek. You guys are actually sharing what you're doing, and you guys are doing, and then there's a lot of propaganda, like the Chinese government saying that, well, we're doing this for humanity. But anyways, I don't know. I mean, it's nice to get a look into these things. I was, I mean, I'm essentially neutral, but yeah, 3 cheers for DeepSeek. So, what are the DeepSeek papers? So there's been a whole set of papers that have been coming out of the DeepSeek group, and the one thing to keep in mind is that they have their version 3 here. So they have a really powerful innovation that we're not going to go into, but I think it's really maybe at one point I will go into. But anyways, it's multi-head latent attention. So they have a way that they've kind of done a basically 57x reduction in the basically the computation cost of doing attention. Okay, and it's based on some fancy linear algebra, but this is really kind of a big deal. And they also did a bunch of innovation where they were able to kind of share things out among multiple kind of GPU clusters. They had some innovations in terms of how they ran the models. Because of course they were under this kind of export control where they can't get the latest and greatest NVIDIA chips. Not to say there aren't other efforts in China that are looking into chip fab. But anyways, I mean, what I think really freaked people out was that were the claims, and I think this, of course, was a big savings here. But the claims basically that they show that you can do this, you can work in this area without having to like buy that many NVIDIA chips, and you can kind of do it with less resources. You can use your brain instead of just kind of like jacking everybody's like throwing money back, round tripping, like all these oligarchs round tripping their money back and forth between OpenAI and NVIDIA. You can use your brain instead. So that's what they did. But anyways, so the interesting thing is they directly applied reinforcement learning without any kind of SFT. So they just this was their DeepSeek R10, which is kind of it didn't get the best results, but it's very innovative because it just said, forget this supervised fine tuning. We're just going to do the self-verification. And then another thing also it did when it prints out its traces, it doesn't hide the reasoning steps. So one thing that OpenAI did is they didn't show the reasoning steps. They just kind of kept those kind of secret. But they would just kind of give out the results, or they would kind of they would give out some of the reasoning steps, but they would there were a lot of the wasted tokens where you weren't seeing kind of what was coming from them. But with R10, you can see much more of the steps. You can see kind of behind, you see kind of what it's doing. Yeah. And so we'll come to it in a second here, but kind of some of the stuff that they did. But the interesting thing is they just tried to bootstrap something up just directly from using reinforcement learning and no supervised fine tuning. And then they did some other stuff here where maybe I'll come back to these things. Right. Yeah, but yeah, they generated strong evaluation results. Again, the evaluation results are here. So that's kind of the first page of the DeepSeek paper, DeepSeek R1 paper. So that was the one. Got everybody's attention with that. Also, another thing to keep in mind here is they are just on the open source side of it. They have an open algorithm and the weights, so they share their weights, but they didn't share their exact training data. Okay, so they held back something. So there's always a catch. So let's just kind of like this. I'm not going to be able to say too much about this, but just kind of maybe people who want to study it, they can kind of look into it. But basically, what this has to do with this they're using something that's kind of a reformulation of the of the proximal policy optimization work. What they're doing here, and it's called group relative policy optimization. The key things to keep in mind here, so these are it's like you're trying to maximize this thing. This quantity you're trying to maximize. So what you do is basically you generate a set of outputs. See, that's what the group is. The group is like, I give it a particular question, okay? So maybe a reasoning question. And then the system is going to generate a set of outputs. These are like full completions out to a solution from the old policy. So this is your old policy. And then what we want to do is we want to do, so let's see here. We have a reward model that basically, let's see if I can talk about the reward model is. I might have to kind of do that before I show this thing in detail. Right? Sorry. Okay. The reward modeling is basically the, okay, so let's just kind of see how this might kind of, I'll kind of do this in a little bit strange order here. So when we talked about like the question somebody had about what does do we get rid of the chain of thought prompting? No, this is the prompt that goes into DeepSeek. So you said that, say a conversation between the user and the assistant. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process in the mind and then provides the user with the answer. The reasoning process and answer are enclosed within think tags and answer tags, respectively. Think reasoning process here, think answer here. So it's kind of redundantly saying that. User. Now this is the prompt here. This right here is like the question of like, all right, I have a math problem where here's the combinatorial thing. Give me the seven, give me all the X and Y's that satisfy such and such. That's what this prompt is here. That's what gets substituted in right here. But this whole thing winds up becoming the prompt. And then it's assistant. This is like kind of assistant. What do you say? And then it does the completion. So this is the exact prompt template that goes into DeepSeek. And then this gets filled in with the actual problem. Okay. So this is kind of a chain. This is kind of a prompting technique, kind of a similar to think step by step, but it's being more specific about what tags to use. Okay. Now, when a DeepSeek model will take that and will actually generate a completion, then we're going to have a critic. I'll put critic in quotes because the critic actually is not an LLM. It's not a big neural network. The critic is just something that goes and does the following. It's just a little piece of code that will go through and basically say, hey, was the right answer from that math question, is that what is in the answer inside the answer tag? Let's judge whether or not it got the right answer. Okay. In the beginning, probably it doesn't get the right answer. It's kind of harder, right? But okay, but when it does, it's going to get a big reward. Okay, so the reward model is going to say that gets a big reward. Then it also gives reward for correctly formatting. So are you putting stuff in the think tags, and are you separating out as a chain of thought type of completion? It's going to basically go through and just kind of score the format. So this is all that the critic is doing in DeepSeek. So it's very simple, kind of deterministic critic. That's what it's doing. Okay. So so that critic, then what that does, that gives you a reward value for each completion, right? Or and the completion might be partial. It may not be an answer, so it won't give you any accuracy reward. It'll just give you format rewards. That's all it's going to give you. So that's the reward model. That's like R. Okay, in our earlier talk about, when we talked about reward models, you can take any state, any completion, any prompt completion pair, and you can score it based on this right here. Okay, it's kind of probably going to be a lot of zeros. Maybe you'll get a little bit there for that, but that's what it is. Okay, so now this is kind of this right here. This is called advantage. But notice this is that advantage, all advantage is this is the reward right here coming from that reward model or that critic, if you want. It's not a model, it's just a piece of code that just evaluates the thing. And it kind of normalizes that. So that's what the advantage is. It's the normalization of that. So now what goes on here is that you're simply saying how much we have a set of different completions. How much better, let's say we have a completion that has a high advantage, it has a high reward. So then that would basically be if this value right here, so the probability that this completion is going to come out is greater than the probability that this is going to come out in the old one, then if this is a high advantage, that's gonna really boost our overall score, our overall result from the group, right? So the point is that what if these are a high advantage, so they're good rewards, they're good completions, and our new policy winds up boosting them, then whatever this proportion is over how much it boosted it earlier, that should determine how much this contributes the to how to the reward this determines what goes into the policy optimization. So that should be favored. So basically, if that's happening, if this is a high ratio, so this is like the probability now is much higher than it was in the last iteration, and it's got a really good advantage. That should really contribute toward the showing that that changing the policy in that direction is a good thing. However, what these clip things do, this right here does, this just basically says, okay, don't get too wild. If the ratio here is too high, if it's got too much of a tangent, or if the slope is too high, then don't go hog wild, don't go too far, because you want to clip it. So there's just kind of a something that you do in terms of making sure that you don't kind of bounce around too much. When gradients are really high, you want to clip them. That's kind of just like practice for stabilization. And then this KL divergence term is also the same kind of thing. You don't want to like just reward hack it. You don't want to destroy everything. So basically, all this together, if you study it, is kind of what guides the reinforcement learning. Okay, so I hope that was at least somewhat clear. So what does this tell us then, or what does it show? This is kind of what they were showing. This is showing that this is actually what this is okay. If A is greater than this is the prompt that goes in. The prompt that goes in is this thing, and then this question substitutes in here. And that becomes the prompt that goes in. And the question is, if A is greater than 1, then the sum of the real solutions of this right here is equal to some value, right? So this is not like this is like kind of like a plug and chug kind of math problem. So it's like I don't know. Anyways, but here's the thing. Is that this whole like going through and then wait, that's an aha moment I can flag here. This is actually what came out of R1. And this is showing a backtracking. This is showing that it's learning backtracking strategy. Okay, so this is quite impressive that it was just able to learn that. And then another thing to show here, now my slides are kind of out of control here, was this right here. So this is really pretty impressive or pretty interesting. So what it says, this is the pure reinforcement learning based approach. And what's happening here is that the more iterations we do in the learning, then the average length of the response is going up and up and up. So as it's learning more and more and more, it's providing longer and longer completions that are showing the thinking steps. Okay, without any kind of SFT data. All right, so that is very, very promising. Okay, so let's go back to this right here. And I mean, there's a lot more going on in the deep papers, but that I think is something to, this is okay. So they showed some other novel pipelines. So basically what they did, excuse me, there were some language mixing problems and some other kind of problems where like, if you take DeepSeek and then you basically that R1 and then you basically ask it questions that are kind of just things that are going back to the, like, okay, well, all right, there's all these reasonings, but then I ask it like, all right, what's the capital of Taiwan or something, or what's the capital of Mexico or something? It will start doing a reasoning problem. So it's like, okay, it's kind of gotten a little bit wild there. So basically when they look at DeepSeek R1, there's like several variations in the paper, but one of them is they try to correct this thing. So it also might be that you give a question in Spanish and then it hops over to English. It's like you prefer for it to give the answer in Spanish. So there's these kind of language mixing problems, and there's this problem of just being able to actually ask non-reasoning prompts also. And that's something that they kind of fixed with a novel kind of pipeline. data pipeline. So they have a really complicated pipeline with building these other type of models, and it's like I don't think it's worth it to go into too much detail on, but it shows you that like what is involved in cooking one of these things up. So it is kind of like there's a very elaborate kind of process to go about kind of getting all the hyperparameters, getting all the architectural kind of decisions made. So there's a lot involved with actually building something up that can go into quality production. So there's a lot of, again, like I said, a lot of black magic in the whole area. Right. So, yeah, so DeepSeek was really good because I think it shed a lot of light onto how teams go about doing this. So it was kind of nice to see that because OpenAI wasn't gonna share that. Okay, so now just recently we had this issue that came up, this illusion of thinking paper, which I put in the readings. This is his Apple paper. And the thing about this paper is that, yeah, well, let's just see what it showed. Okay, so first of all, this is the Towers of Hanoi problem, which is kind of a classic problem in logics and in planning. So Towers of Hanoi is basically how do you move, like the rules are you have to always have it so that if you're going to have a disk, a small one has to be on top of a big one. And you can kind of solve arbitrary problems, but this is like a simple little case of well, you want to move this. The goal is to kind of get 1, 2, 3 onto the third peg, but it starts on the first peg. So basically, you're saying, can you take the moves that will move the disks with respecting the the constraint that only small disks you cannot have a larger disk over a smaller disk. Do the operations that will take you to the final state there with three disks. And so these are the moves that when you say think and then it moves. Okay, it might do a double check, whatever, but the final moves are this. They did a bunch of different problems, but the Tower of Hanoi I think is a really good, simple one to kind of start out with. And they were doing it over Claude. And so they did Claude, like the Claude 3.7, I believe, is the one that is just like a standard LLM type approach. Claude 3.7 plus thinking is the one that has a reasoning model also built in. And what they showed here is they showed basically that they both of them collapse pretty much when you get up to 5 disks. So you get up to enough disks here, then it breaks down. It doesn't give you the proper solution. And then the response length in terms of tokens really kind of goes up for the thinking model. So it really gets expensive in terms of it's out there flailing around looking for some kind of solution, but it's already got out to like 5 disks, and then it's kind of starting to well, it does a little bit better, but then they when you get to 10 disks, they both fail. They both suck. But all of them. So what it was interesting is that they've noticed this thing going on, at least with Claude, I guess. They've noticed that it gets up to a certain point, and then at one point it just fails. It kind of falls off. Yeah. So what do we take from this? I think that I don't know really how definitive this is quite yet. The one thing that's a little bit problematic with all these kind of studies is they're evaluating over Claude, which has, I'm sure, a lot of secret little switches in it. So this whole business over here of like the break off here, I'm not sure. It's harder to kind of it's hard to kind of determine it, but it's an interesting paper, and it's definitely timely. A lot of people are debating it or have been debating it, but next week I'm sure there'll be something else that will be debated. Okay, so let's just conclude here. Yeah, so as we saw, there are many species of reasoning. So reasoning is like it's really very broad topic, it's very deep, very AI. I mean, it comes from philosophy. I mean, philosophers have been thinking about this for thousands of years, and then mathematicians and AI people have been looking at it for quite some time as well. So a lot of the classic AI stuff looks into reasoning, usually under kind of logic cases. Interestingly, one of the Towers of Hanoi was one of the examples in the illusion of thinking paper. Another one was Block's world, which is a very classic AI, Block's world. It's really an active area. I mean, last 1 or 2 years have seen great progress. So we have a lot of additional techniques that are coming online, lots and lots of new techniques. We have a lot of better and better benchmark results. And then we have more real world use because people are using O1, right? So O1, rather the way they write it is O1, it's been available. I don't know when OpenAI made it available, but well, it was after last September. But people have been using O1 to kind of like see what they can get out of it. It hasn't, as far as I understand now, it hasn't really discovered anything new. So it still like seems to kind of almost be mimicking what it sees in the data sets. But the argument or we have a whole bunch of different questions here. So let's just look at this first question. I think that'll relate. So in what areas will RL-based reasoning become truly superhuman? Okay. So AlphaGo is a positive example of this. So AlphaGo, when it was self-playing Go games, started doing things that even master Go players had never seen before. So it was like, wow, it really kind of went superhuman. Of course, chess has also been superhuman, and chess didn't even require a reinforcement learning type approach, just kind of grinding out the game tree. But in game playing, I mean, there's been it's been showing that they're getting better. When will like the world poker champion be a computer? It's probably going to be based on an RL based approach. But the question about reasoning is that, do we have an example yet where a reasoning model has really shown a novel, impressive mathematical like proof result or something? I don't believe so, but I do want to make one mention. This is not the first time this kind of stuff has been considered. So even back, there was it's kind of a search-based solution, I believe, called Mathematical Theorist way back in the 70s, I believe, that shortened one of Russell's proof in Principia Mathematica, and then there was also so it discovered that Russell could have done one of his proofs in one step shorter, which of course is like, okay, it found that, but it's not. I think they tried to get a paper off of that, and then it got rejected. People were like, okay, yeah. I mean, it's kind of like a very syntactic kind of thing. But the question, of course, would be that with reasoning, will we get to a point where mathematical or even computer science type, or like mathematical, like proof, like they're actually proving things that were beyond the scope of our mathematicians? That's the question. Is that going to happen? But even like you have to understand, a lot of modern mathematical proof and all that, they do use the computer to kind of enumerate cases and like real kind of case-based aspects, like where you have to kind of break down by cases, all these different cases and trace them all down. People are already using like assistants to do that. They have been for a long time. But the question is that will we actually just get this kind of exotic kind of super brain that comes out of this reasoning training that does something along the lines of AlphaGo, where we're now getting, solutions we could not have access. I guess it'll probably happen, but the question is to how broad will that happen? To what extent will it happen? So this protein folding stuff. So somebody was talking about like the need for a lot of computation. Is there any breakthrough in that area? And the answer is not really. I mean, there's no fundamental breakthrough when it comes to algorithms, and that's the whole point. I mean, it's like parallelism doesn't really help. I mean, in terms of algorithmically, I mean, you can't take something that you can't solve a problem that is exponential. I mean, you can solve there are games you can play. You can like do stuff like approximation. It's like people are closing on those things, but it's very, very difficult to. There are a lot of problems that are just they have a nature to them, like circuit minimization. Like we know this from algorithms. I mean, there's certain problems that just like, well, I mean, you might be able to do approximation for. You might get to a pretty good solution, but you're not going to get the solution. I mean, we're getting Moore's law. It's continuing. I mean, Yeah, I mean, the more computation power, the better, of course. But the thing is, again, if DeepSeek taught us anything, is that we can't just be like those dum-dums who just take a big, like, a big fat pig with a big wad of cash and just plop it down on the table and say, I want to buy more computation. Um, that's dumb. I mean, I mean, just like, oh, and then think we're going to fire up all these nuclear power plants just to like grind through. I mean, I think we should maybe try to use our minds a little bit more. I don't think there's going to make that much of a difference. I mean, like if things truly are algorithmically blocked, then throwing more computation at it is going to maybe like make n go from maybe like two more places. But I don't know if there's like a real fight though. I mean, it's like kind of like that there's some competitive advantage you can get from going out a couple more spaces, maybe. I do know that one thing that was kind of a pure play that they were talking about, like this has to do with more quantum computing, which I thought was really interesting. And that is that like quantum computing actually does have a chance to, that might actually have be the ticket. That might be the using our brains kind of aspect to it. But there was something where they were talking about like network providers optimizing like their packets. And it's kind of a pure kind of business case where it's like, look, if I take all your stuff and I give you a better algorithm to do your scheduling or to do your kind of like packet planning or whatever, like the way you do things, and I can show you systematically that you're gonna operate your system with 10% less, resource cost because we've been smart about it, we've optimized things. Well, that translates into a direct business case where it's like that's going to save you that amount of money. How much are you willing to pay for this? So there's a nice kind of purity to like coming up with kind of computational innovations. But I don't know. It just sometimes feels to me like you got a bunch of dummies who are just like basically, or they think they're so smart, but they're just basically calling in, this thing. We have enough capital to kind of solve these fundamental problems. And it's like, well, I don't think so. They're fundamental problems, you can throw money at them, but I just have this intuition that's kind of skeptical of those kind of arguments. But yeah. Um, all right. So then on the illusion of thinking kind of thing, then the question is like, well, what really are the limits, and how do we score results that are really not truly verifiable? So maybe like the kind of question is, can we get our little turtle? So in the future, little turtle is going to get like an RL component kind of built on top of them. We're going to have an RL little turtle RL, and the question is, can we learn some kind of like a generalized solution to towers of Hanoi? Because if you look at the code that actually implements a general towers of Hanoi, they can move n disks, then it's not that much code actually that does it. But how do we deal with the fact that it's not really verifiable? So somehow or another, trying to kind of go up into another abstraction layer in terms of what the kind of solutions are and how they're being verified. I think something in that might be helpful. And then of course, the central question, or the question that we will actually address at one level or another in the sequel of this course, or in the, when I say sequel, I mean the next part of the course, the second half of the course, is that how can reasoning models contribute to the questions in the second half of this course? Can we rig them up to get them to do and to help? I'm not sure how far we'll get with it without Turtle RL. We need Turtle RL to kind of to get anywhere, but maybe yeah. I was debating kind of saying offering extra credit to the student who can like over next. Can somebody kind of like take the RL stuff that we did in recitation 2, take Turtle and actually implement a really super simple PPO or even GPO, GRPO on top of Turtle. Well, if anybody does that, I will give them extra credit. But I'm not sure if I want to officially, announce that. I probably have to do it myself. But yeah. So anyway, so many questions, and yeah. So if anybody has